lectures we were discussing how to write angular momentum and about the fixed point, about the center of mass, and also about any arbitrary point P. So once you obtain the angular momentum, you have to use these equations which is given like sum of all the moments about the fixed point should be equal to the rate of change of angular momentum, either about fixed point or about the center of mass. You see the second relation. Before we do that, there is one important thing which I would like to emphasize. You see, in the previous few lectures, we understood the expression of angular momentum as expressed in a particular coordinate system. So let's say you have some coordinate system x, y, z. At this point of time, we are not concerned whether it is body fixed or not body fixed. So in this coordinate system, let's say one which is centered at G, please close the door. Which is centered at G, you can write the inertia tensor. You write the inertia tensor, and we found that this inertia tensor can be simplified by a suitable choice of coordinate system. What was that suitable choice? Principal axis. So in principal axis, the off-diagonal terms were 0. So when you write about a certain axis which is known as the principal axis, the angular moment inertia tensor diagonalizes. But the problem again comes into picture when you start thinking about differentiation of this expression. So suppose H dot, if H is, let's say, inertia tensor, now here I am not writing G or O, it can be either G, it can be either O. So when you take the time derivative with respect to a fixed axis, dH, dt, so that you can write H dot. If your coordinates are such that the inertia tensor, changes. Suppose this coordinate is a rotating coordinate and it doesn't rotate with the body. So we have seen that it can, in this coordinate system, x and y and z will be all time varying. If you forget, you can look at this example of the phone. This is the phone and these are the principal axes, up like this and like this. Now if I don't allow my coordinate system to rotate with the phone, then what will happen? Whatever was the moment of inertia tensor at time instant t, when it is, my phone has rotated, my coordinate system, let's say, is still the same, but now the moment of inertia tensor now will be non-diagonal. That means non-diagonal terms will be now present, because for this orientation your initial choice of axis is not principal axis. But on the contrary, if you allow the axis to change with the phone, you rigidly attach the axis, then with respect to this axis, the dimensions of the phone, they remain the same. If you rotate, the axis also rotates, and ix, x, iy, izz, they remain constant. They are time invariant. So if it is time invariant, mostly this time derivative will now operate on only, it will operate only on omega dot. Okay. So this is one advantage of body fixed frame of reference. But there is one more. Please shut the door. Shut the door. So one important point to note here is this time derivative is on omega only if this is not a function of time. This is not a function of time. I shouldn't write like this. Let me write. The inertia matrix is not a function of time if it is body fixed. So that's why we are interested in body fixed coordinate system, because when you take the time derivative, the inertia matrix becomes constant in a body fixed frame of reference. But there can be still problems if you choose body fixed frame of reference, which we will now discuss. Okay. Sometimes inertia matrix will become time invariant in body fixed, but omega will start changing in that particular frame of reference. How? So let us look at this case which you have discussed time and again. You have a shaft like this, and revolving around this you have another, let's say, a rotor which is mounted rigidly on this shaft. Let's say you have a rotation like this, and you have a rotation like this. So there is a vertical shaft, and then there is another horizontal shaft mounted on the vertical shaft, and on this horizontal shaft you are having a rotor which can rotate, spin about this particular axis. So you can choose some axis. You can name these axes as, let's say, X, and you can call this Y. This is the fixed point O. This is the mass center G of the disk. Now here, if you note carefully, let us install a body fixed frame of reference. We say that X and Y, they are attached to the rotor. They are attached to the rotor. Attaching to the rotor does not mean that necessarily it should be on a physical point on the rotor. What I mean is that this reference frame will have the same angular velocity as the rotor has. So, what is the angular velocity of the rotor? It is v, and it is this. By now, you know that the total angular velocity of the rotor is this plus this. And what will be then the angular velocity of x, y, z? It will be same as that of the rotor. With respect to any inertial frame, capital X, Y, Z, it is. So, whatever is the angular velocity of the body, that is also the angular velocity of the frame, and we call this the body fixed frame. Why we want the frame to be body fixed? So that this inertia tensor is time invariant. So you want your inertia tensor to be time invariant. There is a catch, however, if you write the angular momentum about a fixed point. Let's say we want to write angular momentum about this fixed point. So what can I write? HO, and we using the body fixed frame, of course you will write I, okay, I about this. So whatever you have the centroidal axis, you have to use the parallel axis theorem to write angular momentum about this fixed point O. And then the angular velocity vector, which you can also write this as Pi and sigma j. So this will be P, this will be sigma. This will still be the principal axis. I mean, because one of the axis is still principal axis, others will be just shifted in. Because if you construct, imagine a parallel axis to this is a principal axis, you are shifting it. So only the diagonal components will shift. Which component will not undergo any change? That is the x component. How do you understand? You rotate disk about G, about x axis, it's the same. You rotate the disk about x axis about O, it is the same. So Ixx remains unchanged. So the parallel axis will apply to y, Iyy and Izz. So you have some Ixx, you have some Iyy, and you have some Izz. Rest are same. In the body fixed frame of reference, if you want to conceptualize this angular, now this is finally a vector. You can write the vector as Ixx P I cap plus Iyy sigma j cap. Yeah, you can use the transfer theorem also. So you can write angular momentum about this set of axes centered at G, and then you use the transfer theorem. So you can use the transfer theorem also. But if you don't use the transfer theorem, the result is embedded in the parallel axis theorem. So if you look at this angular momentum in this frame, you will find, can I write it component wise? Ixx P I cap. So there is some Hx I cap, and there is some component of angular momentum Iyy sigma j cap. So I can have an angular momentum vector written here in this body fixed frame. Kuch hai, I don't know, I have to compute. And similarly, you understand that there is a omega also. In this body fixed frame, we have written the angular momentum HO and we have written the angular velocity vector. दोनों इस frame में लिखा हुआ using the x and y and z, which is the body fixed frame. And this frame rotates with respect to an inertial frame with p plus omega. This is the angular velocity of it. Now close your eyes and picture one thing. Frames को आप भूल जाओ. Forget the frames. You know how this capital omega is moving. How this capital omega means तो क्या बोलते? Omega, total omega of the body. This is the total omega of the rotor. How is this moving? क्या बोलते हैं उसको? Space cone. Very good. So this is the space cone. That is the absolute motion of this omega. तुम कौन सा फ्रेम यूज कर रहे हो ओमेगा देखने के लिए? बॉडी फिक्स्ड फ्रेम ऑफ रेफरेंस जो है, that is moving with this, but it is also having this as the angular velocity, two angular velocity it has, one about the vertical axis and one about the x-axis. Are you getting it? Suppose my question is, someone in the body fixed frame, will he see omega to change or it will not change? जो बॉडी फिक्स्ड फ्रेम में बैठा है, यानी कि x और y और z फ्रेम में बैठा है, how will he see that omega? And see as a constant. Anyone with a different answer? Remember, body fixed frame is not only just rotating like this. ये ओमेगा कैसे है? सपोज ये मेरा हाथ को ओमेगा ले लो, तो ये कैसे मूव कर रहा है? ऐसे मूव कर रहा है ना, तभी तो ये स्पेस कौन ट्रेस करेगा? I don't know whether I've inclined it enough. Now is it fine? And this is my axis. I rotate by omega. But body fixed क्या है? Body fixed ऐसे भी rotate कर रहा है और P भी rotate कर रहा है. So what will happen? How will he see omega? One answer is it will be constant in the body fixed. Anyone who has a different answer? Right, very good. It will rotate about the body cone. So someone rather opposite to the P sense. P का जो sense है, उससे omega is fixed like this, and P is how P is rotating. It is like this, rotating like this. So someone will see omega rotating in the minus P direction. Because the frame is rotating with P. The frame is rotating with P. Is it making sense? नेगेटिव साइन होगा, क्योंकि तुम्हारा जो फ्रेम है, ये एक्स वाई को एक रिजिड बॉडी समझ लो, तो ये रिजिड बॉडी एक तो ऐसे रोटेट कर रहा है और दूसरा एक्स के अबाउट में वाई ऐसे रोटेट कर रहा है. तो एक तरह से इसको और इजीली कैसे समझ सकते हैं? एंगुलर मोमेंटम का जो वर्टिकल कंपोनेंट है, दैट विल स्टार्ट ट्रेसिंग अ सर्कल in P sense, but opposite to the P. माने P magnitude wise, but opposite to the sense of P. Because you are rotating with P. और ओमेगा का एब्सोल्यूट जो मोशन है वो P से रोटेट नहीं कर रहा है, वो किससे रोटेट कर रहा है? इससे रोटेट कर रहा है. तुम्हारा फ्रेम में P है, because you are choosing body fixed frame. So it is like, suppose this is your x and y, और ये है ओमेगा. The green marker is the omega. So this is rotating with P. ऐसे रोटेट कर रहा है, तो जो यहाँ पे बैठा है वो क्या देखेगा? P is moving in a reverse direction. Kinematic inversion जानते हो? पढ़े हो कभी? It's the same thing. I am doing a kinematic inversion. Someone in this frame, because this is moving like this, so if someone is there to make the same relative motion, I do a kinematic inversion and it will